Hello, truth seekers, welcome to Cruise TV, your #1 YouTube channel that provides you with facts, with zero to very minimal errors. Do the Atlantic Ocean and the Pacific Ocean mix? Truth seekers. First of all, mixing in the ocean isn't as simplistic as two fluids with different properties forming one single fluid. In a fluid system as big as the ocean, there are different length scales associated with mixing. That is, the amount of mixing depends on the scale or size of the water body being referred to. It's not two oceans meeting, it's glacial meltwater meeting the offshore waters of the Gulf of Alaska. The reason for this strange phenomenon is due to the difference in water density, temperature, and salinity of the glacial meltwater and offshore waters of the Gulf of Alaska, making it difficult to mix. While we've given our planet's oceans separate names, in reality, there's no border between them, and currents continually flow between them and mix their waters. The Atlantic and Pacific Oceans meet at the southernmost tip of South America. In this region, a strong current carries water from west to east, sweeping water from the Pacific into the Atlantic. Truth seekers, it's normal to ask how can they have different densities if they're both waters. The difference in their densities is a function of varying salinity concentration and levels of temperature. The Pacific Ocean is connected to the Atlantic Ocean by a 48-mile waterway in Panama known as the Panama Canal. Panama is the narrowest landmass between the two oceans, and the canal consists of 3 locks and dams enabling the passage of ships from the port of Cristobal on the Atlantic side to the port of Balboa on the Pacific. The canal greatly reduced the time taken by ships to cross from the Pacific to the Atlantic. Its construction is considered one of the largest and the most complicated engineering projects ever undertaken. However, the Panama Canal is not the only waterway connecting the Atlantic to the Pacific. There is also a tiny creek in Wyoming where the two oceans merge. Density is directly proportional to mass. And when you put more salt in water, the density of the water increases because of the mass of the water increases. The greater the salinity, the greater it is mass. There is mixing going on at the interface between the two oceans. Notice their color differences. Sky blue color is typical of a shallow tropical shelf while deeper water may look dark blue. But if there are considerable blooms of phytoplankton, it may look green. Before proceeding, truth seekers, let us know in the comment section, why do you think the two oceans do not mix? Well, it's not two oceans meeting, it's glacial meltwater meeting the offshore waters of the Gulf of Alaska. The reason for this strange phenomenon is due to the difference in water density, temperature. Ken Bruland, professor of ocean sciences at the University of California, Santa Cruz, was on that cruise. He said the purpose of the cruise was to examine how huge eddies, slow-moving currents, ranging into the hundreds of kilometers in diameter, swirl out from the Alaska coast into the Gulf of Alaska. Those eddies often carry with them huge quantities of glacial sediment thanks to rivers like Alaska's 286-mile-long Copper River, prized for its salmon and originating from the Copper Glacier far inland. It empties east of Prince William Sound, carrying with it all that heavy clay and sediment. And with that sediment comes iron. Glacier rivers in the summertime are like buzzsaws eroding the mountains there, Bruland said. In the process, they lift all this material, they call it glacial flour, that can be carried out. Once these glacial rivers pour out into the larger body of water, they're picked up by ocean currents, moving east to west, and begin to circulate there. This is one of the primary methods that iron, found in the clay and sediment of the glacial runoff, is transported to iron-deprived regions in the middle of the Gulf of Alaska. When you look at seas and oceans on the map or from outer space, you might think that they just flow into each other. On the surface, it looks like there's only one big giant ocean and scientists just gave different names to its parts. However, these oceans are vastly different. While we've given the oceans different names, in reality, there's no physical border between them. Ocean currents continually flow between them and mix their waters. The Atlantic and Pacific Oceans do meet at the southernmost tip of South America. In this region, a strong current carries water from west to east, sweeping water from the Pacific into the Atlantic. You may be wondering, what about the viral photo circulating online that showed two different colored bodies of water drifting alongside each other? The fact is, the photo was actually taken in 2007 by Ken Bruland, a researcher at the University of California, Santa Cruz, who was studying the phenomenon in the Gulf of Alaska. Bruland debunked the photo. He later told Snopes that the phenomenon shown in the photo is what occurs when glacial rivers, carrying lots of sediment, flow out into oceans. The photo showed light-colored, sediment-rich freshwater from melted glaciers meeting dark, salty ocean water in the Gulf of Alaska. Before we get into the science behind this strange phenomenon, it is important you first understand the concept of ocean clines. Clines are layers within the ocean that have different properties than the surrounding water. They vary in temperature, salinity, density, or chemistry. The first layer is thermocline, a cline based on the difference in water temperature. It is followed by chemocline, a cline based on the difference in water chemistry, and pycnocline, a cline based on the difference in water density. The reason why Atlantic and Pacific Oceans don't mix is due to several factors including ocean clines, Earth movement, the difference in the direction of ocean flow in the Atlantic and Pacific, the strength of molecule connection, or surface tension strength, and thermocline. The Pacific Ocean has different densities and chemical makeup, level of salinity, and other qualities. One can see by their color that they are far from being the same. Haloclines, the borders between waters with different salinity, are the most spectacular, and this is what we see when the Atlantic and the Pacific Oceans meet. Haloclines appear when water in one ocean or sea is at least 5 times saltier than in the other. Another important difference between the two oceans' water is the strength of molecules connection or surface tensile strength. Maybe they could gradually start mixing with time, but as the flows in them have opposite directions, they just don't have time to do this. Finally, there are also thermoclines, borders between water of different temperatures, like the warm water of Gulf Stream and much colder North Atlantic Ocean. However, the rate of mixing isn't strong enough to completely homogenize both water bodies together. In a fluid system, mixing as big as the ocean has volume scale and time scale associated with it. The duration and amount of mixing depend on how big is the water body. Where the rate of mixing is directly proportional to the square of the volume scale over time scale, implying to consider the size of the fluid parcels in a given time. If we are going to mix about 1 cubic meter volume of water, or even less, then the mixing rate will be accordingly shorter. When you increase the volume, it will also increase the duration to homogenize both the water masses. Therefore, the complete mixing of larger water bodies such as oceans with different chemical and physical properties will take a longer time. But they do mix, that's the point. Normally, when water is heated, it will expand, therefore increasing the volume. Since density is inversely proportional to volume, the greater volume will lower its density. When comparing two samples of water with the same salinity, or mass, the water sample with the higher temperature will therefore be less dense. Furthermore, the distinct dispersion of their currents, surface and deep water current movements, makes it even more difficult for these water bodies to mix.